To complete our graph of a rational function, f of x equals p of x over d of x, we need to understand the end behavior. Remember, the end behavior of a graph is how it behaves for large values of x, either x going off to the right-hand side of our graph to positive infinity, or x going off the left-hand side of our graph to negative infinity. So far, we have looked at the end behavior for polynomials. And recall, for large values of x going off to positive or negative infinity, polynomials behave like their lead term. Our numerator p of x is a polynomial, so for large values of x, p of x just looks like its lead term, say an x to some power n. And d of x is a polynomial as well, so for large x, d of x behaves like its lead term, say bm x to the m, its degree. Now bringing it back to our rational function, this means that for large values of x, f of x, which is p of x over d of x, behaves approximately like an x to the n over bm x to the m. Now let's look at this in three cases. In the first case, if m is bigger than n, then our function looks like an x to the n over bm x to the m. Just using that p of x looks like its lead term, an x to the n, and d of x looks like its lead term, bm x to the m. Now, we can reduce this because our n powers of x up top will cancel the first n powers of x down bottom, leaving us with just an up top and bm x to the m minus m down bottom. And it's important here that m is bigger than n, so we have a positive degree for x down in the denominator. So now as x gets really large, x to the m minus n gets really large as well, which means we're dividing our fraction by a bigger and bigger number. So the fraction as a whole goes to 0. So when our degree down bottom is bigger than our degree up top, our function just looks like 0 on the ends. Now if m equals n, then our function looks like an x to the n over bm x to the n as well. But x to the n divided by x to the n is just 1, leaving us with an over bm. So in the case that we have the same degree up top as down bottom, our function looks like an over bm on the ends. In the last case, when m is less than n, and the degree up top is bigger than the degree down bottom, then we can use polynomial division and rewrite this as some other polynomial q of x plus r over d, a remainder, whose degree is less than d. Now, for x going off to positive or negative infinity, r of x over d of x just looks like 0, because the remainder has a smaller degree than the divisor d. So we're just looking at case 1. But this means, as a whole, for x going off to positive and negative infinity, p of x over d of x just looks like q of x, because all we're adding in r over d is approximately 0. So if our polynomial has a smaller degree in the denominator than in the numerator, we need to do polynomial division, and on the ends, our function looks like the quotient q of x.